Hi friends, in the last class we discussed about wave equation. In this class we are going into specific waves, means the time harmonic fields. This is an important part when we are getting into the wave propagation and all. This is the basis of our approach when we are discussing wave propagation. So please pay attention to this. Let us see what is meant by time harmonic fields. Okay. Till now we were discussing about the time varying field, right? So when I say time varying field, what does it mean? Like I have a field and which is varying with respect to time. It can have any shape. So that is a time varying field. Like my electric field intensity, if you say, if it is varying, then and it is varying with respect to time like this at a particular position, then I say it is time varying field, right? And our field will vary with respect to time as well as with respect to space, right? Thus we discussed in the last class that if I have a current carrying conductor and a constant current is passing through it at a particular point in space, you will have a we will have a magnetic field. When your space coordinate changes, then your magnetic flux density or magnetic field density will be changing throughout the space. Now if the current which is flowing through the conductor, that is also varying, that also is varying with respect to time, then what will happen? At every point in space, your magnetic field density also will vary with respect to time. So in space, your or this magnetic field around the conductor, that is varying with respect to space as well as with respect to time. That is what we say by what electromagnetic field, or that is what is meant by that. But our analysis was quite general, that your time varying means it can be of any way, the variation can be in any way. So now let us go specific. What we are going to analyze is that time harmonic field. What is meant by time harmonic field? It is something which you might be familiar from your understanding on waves and oscillations. So what it means? It is quite simple. What it means is this much only. What your field, the one that varies periodically or sinusoidally with time. That is what is meant by time harmonic field. If your field is a time harmonic one, that you say when you have a periodic variation of your field with respect to time. So that is what is meant. So that periodical variation, that can be what, for our analysis we will consider it to be sinusoidal. So a sinusoidal variation with respect to time, that we call as what, time harmonic field. Clear? So, and why we are going for that? Why we are going that for? Because whatever wave shape you have, whatever be the wave or the alternating or a period in a periodic wave, whatever waveform you have, all of them can be expressed as what? All of them can be expressed as sum of sinusoid. So again, when we start analyzing our field, once you know the analysis for time harmonic field, you can just elaborate it into all other kinds of fields. So that is why we particularly are concerned, or we are particularly getting into this time harmonic field. Right, you know about Fourier series expansion and all, so that we can apply any waveform. It can be expressed as a sum of what, sinusoids. So that is not due. So now we will get into time harmonic field. And whenever we say time harmonic field, or as I said, it's a periodic wave, then we can use the concept of phasor here. Phasor is a concept which you know pretty well as an electrical engineering student, right? When we learn power system analysis or network theory, all the time you are getting into phasor. So before this our intention is to express our Maxwell equation, right, in phasor form. That is our intention of this lecture. Okay, because why it is we will see, but particularly in this lecture we are going to express our Maxwell's equation. Maxwell's equations now we derived, right, for Maxwell's equation. Those four Maxwell's equation are now in what, are time dependent, that we already expressed, like del cross E equal to minus dou B by dot E, right? All those equations we already wrote, and we understood that they are interdependent and they are what, time varying as well. Well, our intention is to write them in the form of phasor. Okay. So what is a phasor is quite known to you, right? If you have a sinusoidal wave, right, that can be seen as what, a rod which is rotating like this, right? A rod which is rotating in a circle, right? Whatever be the length of this rod, that we take as what, the magnitude of that phasor, right? That this thing you know about this theory. So that animation part you can see here. So the frequency of that wave is related to what, this motion, this rotation of this vector in space. Okay, we can see phasor as a rotating vector in space. The one and only one interesting thing is that it can be adopted for what, time harmonic kind or time harmonic wave. Why? Because it should always run at the same constant speed. Then only we will get the this kind of waveform here, right? So we will think that our frequency is constant or our angular velocity is constant. Okay. Now let us define phasor. In mathematical terms, phasor is a complex number that contains the amplitude and phase of a sinusoidal oscillation. Okay, phasor is a complex number that contains the amplitude and phase of a sinusoidal oscillation. Right. So, how we will express usually a complex number. Z, let us say Z is our complex number, which is equal to what, x plus jy. In polar form, the same can be expressed as what, r angle phi. Just note you, we are just refreshing your understanding on complex numbers and phasors. So the same thing we can express as what, r e raised to j phi, right? Because e raised to j phi again can be elaborated as what, the cos phi plus j sin phi, right? Cos phi plus j sin phi. So when we make it into static, whatever you saw in the last figure as an animation, same thing only here. This r is what, r is the magnitude of that vector. R is given by what, r is given by root of x square plus y square. When you have a vector like is vector x plus jy, then r is given by what, root of x square plus root of x square plus y square, right? So that is the real and imaginary part of that complex number, and r is this. So the angle phi is given by tan inverse of y by x. This all are known to you. So that is how we represented a phasor. Basically, this thing is rotating at a at an angular velocity omega radian per second. Okay, that is our understanding. So whenever it is like every time whenever this phasor quantity, we can really understand a bit better when we have two waves. Okay, two sinusoids when we have, that is the best way to understand it. So let us see, like now I have two phases, both are having the same magnitude. Let us say one is blue and another one is red. So when with respect to time, what happens with respect to time, amplitude we don't have any doubt, right? Root of x square plus y square, whatever the amplitude is, that if we are considering as these two rods here, red and blue, then whatever be its length, that is what the amplitude of the wave, right? There is no doubt about that. Now what is phase, like these two are varying with respect to time, and let me say one is sin omega t plus theta 1, another one is sin omega t plus theta 2. So we with a reference, let us say with a reference, we need to see the phase difference, right? So that is the that is the two parts here. So the same thing, if we when we come into the phasor notation, we will get like this, like we are having some reference here. Okay, that is the that is the reference point here. So we are having some reference here. With respect to that reference, your red wave is what, around 30 degree, there is a phase shift of 30 degree. Okay, means this, it is let me say with respect to the reference, it is leading by a 30 degree here. Okay, so and the next one is leading by around 140 degrees. That is the second, the blue line. Okay, and the phase difference between both of them, there is a phase difference between both of them also. So this kind of representation is what we call as what the phasor representation. Okay, now there are different phasor properties also. when you have it is just like complex number algebra, right? Where when you have two complex numbers z1 and z2 means what, x1 plus j y1 and x2 plus j y2, right? When you have two complex number, when you want to add it, it is better to be in what, this complex number form, this rectangular form, like x1 plus jy1, x2 plus jy2. You can add the real parts and you can add the imaginary parts. When you come into subtraction or into division or multiplication, then you have to multiply the magnitude part, and then the phase part you have to add or subtract, right? Let me say your first complex number is r1 angle phi 1, next complex number is r2 angle phi 2. Then when you have to multiply this, what you will do, multiplication will be what, z1 into z2 means what, r1 angle phi 1 into r2 angle phi 2, that will be r1 r2, r1 and the magnitude parts will be directly multiplied, r1 r2, but angle, how it will be coming, phi 1 plus phi 2. And when it is division, it will be given by what, r1 by r2 into angle of phi 1 minus phi 2. So these things are known to you, so I am not getting into detail now. Okay. So our general representation of a phasor was what? Z equal to r e raised to j phi or r angle phi. So this, in this phi is where we are adding our time element in our phasor, right? Right. This is our phasor representation. Z equal to x plus j phi equal to r angle phi. Okay. And this phi we can write as what, omega t plus theta. Theta is what, theta is like with respect to reference, and even it can be anything, it can vary, means the theta may be a function of space or time, or you can say it as a constant. As we mostly see in our power system analysis and all, theta will be what, a constant value. Okay, it will be independent of it will be an independent value with respect to space or time. Okay. So this phi we can take it as what, omega t plus theta. Now this r e raised to j phi, that is the complex representation, r e raised to j phi. There in place of phi we can substitute omega t plus theta. So I can just elaborate it as what, r e raised to j theta into e raised to j omega t. So that is my complex representation. Now when we take the real part of that, when we take the real part of the real part of r e raised to j phi, then what we will get, real part means what, e raised to j phi we can write as what, cos phi plus j sin phi. So real part will contain only cos part. So in terms of phi we can substitute what, omega t plus theta. So it becomes r into cos omega t plus theta. Okay, that is the real part. And imaginary part will be what, that will be the sinusoidal part. So real imaginary part is r sin omega t plus theta. Clear? Now in the similar fashion, let us consider a current. Okay, we have a current which is varying with respect to as a sinusoidal wave, it is varying. Okay, we have a current like this. Okay, it is sinusoidal, it is varying. So it's a cosine function. So let us say it is going like this. Okay, not exactly 90, and there is some theta also. Okay, fine. So this is a cosine function with respect to time, I of t. Okay, so the same I of t, the same current I of t we can write as what? This is I of t means what, I0 cos omega t plus theta, right? So this that in complex that in complex form we can write as, means IOT can be written as what, the real part of I0 e raised to j theta e raised to j omega t, right? Because the complete I0 e raised to j theta e raised to j omega t will become what? Is erased jx, if we elaborate, cos x plus j sin x, right? So similarly here it will become what, I0 into cos omega t plus theta plus j into sin omega t plus theta, it will come. So when you already know that your current is only how much, only the real part of the cosine part. So we put real part also here. So it can be written as what, real part of I0 e raised j theta e raised to j omega t. Clear? Now if you have the let me say this is omega t, it depend on what, the frequency of the wave. When you have a periodic wave, the frequency of the wave, right? So when you have several number of currents at the say at this frequency, or at this frequency, what will happen? what happens is that every time you will have this e raised to j omega t term with every vector. Let me say another current I1t, okay, cos omega t plus theta 2, okay. Then also what will happen, this e raised to j omega t will term will come, okay. What it represents is that this vector is rotating at what, or this part represents frequency. So we can take out that part, and the complex term I0 e raised j theta, this is called as what, phasor current, and we denote it by Is. So understood. We are just what we are doing by phasor representation is that here we are just avoiding this time variance, or we are just avoiding the time variance term in this, or we are making it time independent, okay. Means it is really the e raised j omega t part when it comes, when the e raised j omega t part is coming, what it represents, it represents that with respect to time, when you are when it's a function with respect to time, your function is varying, right. So the same current only, since this part does not since we have a time harmonic field, since this part will not affect our understanding, right. So Is will become I0 e raised to j theta, the same we expressed as what, I0 angle theta, okay. So this I0 angle theta, or I0 e raised j theta, this is what we mean by what, the phasor current. Clear? Now once you know the phasor current, when you want to have the instantaneous form, what you should do? You should do I of t equal to real part of Is e raised to j omega t. Right? Is is already I0 e raised j theta, into e raised j omega t will give you the complete I of t. Right? Real part of it. Now you can ask a question like, why I should not use imaginary part, right? Even in imaginary, why I should not use imaginary part? Okay, you can use, but once you are following one custom like real or imaginary part, then you should stick with that. That is the only condition. Okay. Now this representation, current is a scalar, right? Even in electrical engineering up to now, we have used the phasor representation only for what, a scalar, right? But when you take potential, current, or any other quantity, you use phasor representation for a scalar. Frankly, we can adopt the same for a vector also. We can adopt the same for a vector also. Okay, but there are conditions, like you cannot just take it for any kind of vector. You can take it for a harmonic field vector. Okay, when you, as I said before, when your vector is periodic, then you can use this phasor representation. Okay, so consider a vector A. Vector A means what? Our vector, when it is time varying also, already our vector is what? Space, with respect to space it is varying. So it's a function of x, y, z, the space variables, and now it is also a function of what, time, when it started to become the time varying. Now here it is particularly what, time harmonic field. So we are representing it in which form? Phasor form, as what? As x, y, z. The difference between these two terms, this is why we are getting into this. Here our vector A, our real vector A, that is what, that is a function of x, y, z and time, means space variable as well as time. But when we are changing it into the phasor form, it is only a the function of what, x, y, z, means it is becoming time independent. Okay, so our analysis will become much easier. That is why we are getting into phasor representation. Okay, now as I said before, it's just similar to our discussion on general phasor. Similarly, our vector also can be represented as what? Vector A is x, y, z and t, a function of x, y, z and t. So that can be represented as what? Real part of some vector As, means what? This is the phasor, vector As x, y, z e raised j omega t. So what is our phasor here? The phasor part is As of x, y, z. Clear? The phasor part is As here, the suffix S represents what? The phasor quantity. So As x, y, z, that is our phasor, the phasor form of the vector. Okay. So phasor is a function of what? Position and not time. Okay. That is the importance here. Now let us consider our vector A. Some vector we have, that which is equal to what? A0 cos omega t minus beta x into Ay. So this is our vector. Okay. Let us just see this function once. Okay, what you can understand here, a0 is some magnitude, some constant value, and it is propagating in the direction of what? Ay means it is going in the direction ay. That much is quite clear. Now inside cos function we got what? Omega t means it is varying with respect to time, and we also got beta x. Beta means what? It is varying also with respect to whom? With respect to the x variable, right? Are you getting my point? So this is the example of a function which is varying with respect to time as well as with respect to space. Okay, you can clearly understand that here. When in my term a0 is a constant, and what inside cos you have got omega t as well as beta x. The t, whenever t comes with respect to time, what your vector is varying, and whenever you have the beta x term also with respect to space also your vector is varying. That is what we are meaning here. Okay, now how you will write vector a? When you write vector a, it can be what? This vector a can be written as what? The real part of a0 e raised to minus j beta x and ay e raised to j omega t. Here these two work together, right? Omega t minus beta x. When we made it into the exponential form here, what happened? We got a term with one kind of variable, which the space variable alone, and we got another term with what? With the time dependence. Okay, since the space variable is here, that is why I am placing the direction also in the similar place. What? a0 e raised to minus j beta x, ay e raised to j omega t. So seeing this, we can understand what will be our phasor quantity for vector a. What will be the phasor quantity for vector a? Our phasor quantity for vector a will be a0 e raised to minus j beta x ay. Understood? Because right, that is e raised j omega t we will omit. Okay, so that is how we get the we get the phasor form, right? Once again I will say this a0 cos omega t minus beta x, right? So if I take this if I take e raised j into omega t minus beta x, that will be equal to what? Cos omega t minus beta x plus j sin omega t minus beta x. So that part's real part only will be what? This a0 cos omega t minus beta x. Okay, so that is what is represented here. That is how we get the phasor form. So the phasor form of vector a is what? Phasor form of vector a is equal to a0 e raised to minus j beta x ay. Okay, this as is not a scalar, it is a vector. This as is not a scalar, it is a vector. So it is the vector, the phasor form of vector a. Okay, as is a0 e raised to minus j beta x ay. We don't need the e raised j omega t part. Anyhow, it is going to be what? Periodical, harmonic, or sinusoidal. So that is not needed. So now if I say take the differentiation of vector a, okay, this is the interesting point. If I take the differentiation of vector a, what I can write, that vector a again I can write as real part of our as, right? As means what? a0 e raised to minus j beta x. I am not I am just taking it as as. Why? Because here my variation is with respect to time, and inside my vector phasor form as, there is no time varying quantity, right? So as I can write as it is, as e raised to j omega t. So now, as I said before, it does not matter about this as. We can take the dou by dot t inside. So dou by dot t of e raised to j omega t is what? What is dou by dot t of e raised to j omega t? Right? Dou by dot means differentiation of what? Differentiation of e raised to kx. What it is? K into e raised to x. So here what we get in front of t is what? J omega. So it will become real part of j omega as e raised to j omega t. I think you are clear here. So differentiation, what we are getting here. So differentiation with respect to time in phasor for a differentiation with respect to time is equivalent to what? Differentiation with respect to time for a vector. Okay, normal vector. It is equivalent to just multiplying it in phasor form. Here the remaining part is multiplying it in phasor form by what? By j omega term. Understood? When you are differentiating with respect to time for a vector in phasor form, it is just equivalent to what? Multiplying by j omega. Thus, understanding also is not new to you. In control systems or in network theory, you have seen this thing, right? When you are like we use the Laplacian operator S, the S equal to what? When you substitute S equal to j omega, you can do that, and you have already learned the how we represent the differentiation in integrator, right? So that understanding is quite enough to understand this j omega term here, that I can convert the differentiation into what? Multiplication into j omega. When it comes to control system, it will become S and all, right? So similarly, so our dou A by dot T is equivalent to what? J omega times the phasor form. Understood? Yeah. So when you are differentiating with respect to time, that is equivalent to multiplying into j omega in phasor form. Similarly, when you are integrating, it will become what? Divided by j omega. Okay. So this is these are the two main part that you should understand, that differentiation of a vector with respect to time will become multiplication of the vector in phasor form with the j omega. Okay, this is the now our vectors are represented in phasor representation. Okay, now this is about this much is our basic concept of a phasor and how we can apply it in vector also. Now let us come into apply this phasor concept to time varying field. Okay, so what are our time varying field? Our time varying field quantities in Maxwell's equations are this much only. What? E, D, H and B. E is the electric field intensity, D is the electric flux density, H is what? Magnetic field density, and then B is what? Magnetic flux density, right? These all are now varying with respect to space as well as time. Okay, we are now in time varying field. So we are going to apply this. For that, first, let us see a Maxwell equation. What is our one Maxwell equation? Okay, we all know what del cross E equal to the third Maxwell's equation, the curl of electric field. Del cross E equal to what? Minus dou B by dot T. So so let us just convert it. Okay, first I am writing it in what the Maxwell's equation in the normal form only. What? Del cross E of what? The vector. This is not in phasor form. This is what? Normal form only. Our vector is a vector with what variables? X, space as well as time variable, x, y, z and t. So here B is written as what? B of x, y, z, t. So for phasor form, what we should do? For phasor form, this vector E x, y, z, t can be written as what? Real part of our ES. This is what? ES of x, y, z. Our phasor form is a function of what? Only the space variables into e raised to omega t. This is what in place of vector A, I am just replacing it with the vector E. Right, in place of vector A, I am just replacing it with the vector E. So similarly, you will have ES here. So ES here. Okay. So if we similarly, this is a vector E, right? So similarly for vector B also, what? Vector B also can be written as this way. Vector B also can be written as what? Real part of Bs x, y, z e raised to j omega t. So this is our phasor. What? Es is our phasor for electric field intensity, and Bs is our phasor for what? Magnetic flux density. Right. So if we substitute these values here into our what? If we substitute these two values in our Maxwell's equation here, okay, in our Maxwell's equation here, what we will get? Del cross E means what? This vector E can be written as what? Real part of Es into e raised to j omega t. Okay, here to be understand the time independence, I wrote x, y, z. Here I am just avoiding that. Okay. Similarly, that will become, this part will become what? Minus dou by dou t of real part of Bs into e raised to j omega t. That is clear. Okay, so what is the left hand side? Left hand side is what? Del cross E, which is equal to del cross real part of Es e raised to j omega t. Es means what? The phasor representation of electric field. Okay, the electric field intensity phasor. Okay, the in phasor form Es. That is equal to what? This now what we are going to do is that Es is already what? Es is a function of what? Space only. It varies with respect to x, y and z. And our del operator is what? Dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap, which is again what? An operator which is going to operate on space variables, right? And this es is independent of time. So when we take this del inside this real part, we can do so. So when we take it, will be applicable to what? Only the quantity which is there which is varying with respect to space only, right? Which is a function of space only, which is our phasor form of electric field, and we need not apply it on whom? This e raised to j omega t part, because right, this is a time part. Okay, so it will become del cross es into e raised to j omega t. Okay, because this we already discussed, because del is not what going to operate with respect to time, they are independent. Okay, now similarly RHS if you take, what is RHS? Dou by dot t of b, dou b minus dou b by dot t, that can be expressed as what? Real part of bs e raised to g omega t. Here this is with respect to time. Okay, so our phasor form bs is what? No, this need not apply on what? Phasor form bs. Okay, there is no need to apply this on the phasor form bs. So I can take what? The minus real part of bs, bs it will not operate. Okay, so dou by dot t of whom? E raised to j omega t. We already know what is dou by dot t of e raised to j omega t, right? So it will become what? E raised to j omega t is j omega into e raised to j omega t. So this will become minus real part of j omega bs e raised to j omega t. I think you don't have any confusion regarding this here. So now let us compare. What is our comparison? Now if we compare this two equation here, right? If we compare this two equation here, inside here, this is LHS and RHS, so both are equal. Inside here you got real part of del cross ES e raised to omega t. Other side you got minus real part of j omega bs e raised to omega t. So if both of them need to be equal, then what should be equal? This del cross ES should be equal to minus j omega bs, right? Because all other parts are just the same. So on comparison we will understand that what? Del cross es equal to j omega bs, right? I am really sorry, it is what? Minus j omega bs. Okay, del cross es equal to minus j omega bs. So when we come into this equation, in this Maxwell's equation, your electric field as well as magnetic field is in which form? Phasor form. Which makes us what is the advantage of that? So this is the phasor form Maxwell equation. Why phasor form? What is the advantage of that? The time factor. Otherwise you have to always deal with the time. Okay, the time in the analysis. So when you are considering a time harmonic field, the time factor is suppressed in analysis while dealing with this time harmonic field, when you are representing it in which form? In your phasor form. Okay, that is why we are doing this. So our phasor, Maxwell's third equation in phasor form is what? Del cross Es equal to minus j omega bs. Clear? That is the phasor form. That is our derivation phasor form. Okay. All other things you can try for yourself how to derive it. Okay, there will not be much changes. Like del dot d equal to rho v is our first Maxwell's equation. Okay, so there is no change. Your d will become what? D will be represented in the phasor form as ds, and the rho v also is what? Rho v also when you come to time varying field, it is varying with respect to space as well as time. So rho v also will become what? Phasor quantity. This is the integral form. Not much changes. Okay. The second Maxwell's equation is what? The non-existence of magnetic dipole del dot bs equal to 0. Right. Here also we have to just change the quantity by its phasor form. There is not much difference. When you come to the curl equations, there is what? Differentiation is involved, right? So here it will become what? Differentiation in phasor domain will become the multiplication with the j omega. So this one is what we derived, right? So there is no confusion on the third equation. Its integral form when you take, it will become what? Es dot dl, which is equal to what? Again it was before it was what? Integral of the surface minus dou b by dot t dot ds. Now that dou by dot t we can take out as what? Minus j omega. It becomes a time independent quantity when it comes to time harmonic field. Okay. The last equation which I did not derive, you can try for yourself. Normally what is your equation? Del cross h equal to j plus dou d by dot t. That dou d by dot t differentiation is equal to what? Multiplying with respect into j omega in phasor domain. So it is just got multiplied. Okay. Similarly in the integral equation, that is our ambient circuital law or the Maxwell's fourth equation. Okay. Once you means there is not much to derive here. Okay, once you are understanding the till the last slide about the third Maxwell's equation, then you can directly apply it to the other Maxwell's equation as well. Okay, so this is the Maxwell's equations in the phasor form or the complex form. Okay. Okay, so with this we are concluding the phasor form of Maxwell's equation. In the next lecture, we will get into what is meant by electromagnetic field, uniform plane waves, and try to get into Poynting vector as well. Okay, with that, I hope in 1 or 2 lectures we will complete the 5th module, comprising of what are basics on electromagnetic waves and uniform plane waves. And for your I will add some questions on complex numbers just to refresh your memory on complex algebra. Do that as your today's work. Okay, so we will see in the next lecture. Thank you.